In our previous work, we've done a lot of applications of integrals, but one thing that's a problem is the set of things that we can actually find antiderivatives for is not very big. So in this next section, we're going to look at a variety of methods which will make our bag of tricks bigger. To start with, I want to remind you of the things that you did with integration back in Calc 1. So this first part's just a review. Some elementary facts. If you want to calculate the integral of a constant times a function, it's okay to pull the constant out in front of the integral and just deal with what's left. If you want to integrate the sum of two functions, f and g here, then you saw back in Calculus 1 that you can figure the antiderivative of f and the antiderivative of g separately and just add them together. A similar fact holds for subtraction, but not for multiplication or division. There is no such nice rule for that. The integral of x raised to a constant power, you increase the power by 1, you have a factor in front that is the reciprocal of the new power, and this works for all n constants except -1. X to the -1 power is 1 over x, and you have to deal with that integral separately. The antiderivative for 1 over x with respect to x is natural log x plus a constant. The previous facts makes it easy for us to integrate polynomials. So if I wanted to find an antiderivative for x squared plus 5x plus 2, I would split it up into 3 simpler antiderivatives. Integral of x squared with respect to x, integral of 5x with respect to x, and integral of 2 with respect to x. The one in the middle has a constant factor that I can pull out. To find a function whose derivative is 2 times x will get the job done. And if you find the integral of x squared with respect to x, it'll have an x cubed in it as the new power, and the reciprocal of that new power has to show up as a factor. So antiderivative is 1/3 x cubed plus 5/2 x squared plus 2x plus c. After you practice a little bit in Calc 1, you didn't bother writing these intermediate steps down. You just write the answer down. We can also do, by algebra rearranging, some problems that are not strictly speaking polynomials themselves. If I wanted to integrate 3x plus 1 divided by x, I would split it up into the two simpler terms, 3x over x plus 1 over x. Cancel the x's out in the first one. All I need to do to find the desired antiderivative is to integrate 3 and integrate 1 plus x and add the results together. So you would end up with 3x plus natural log absolute value of x plus the constant of integration. We didn't bother with the c when we were doing our applications because our integrals were all definite integrals and the constant of integration would have canceled out anyway. Now, if I want to turn the integrand upside down, the integral of x over 3x plus 1, this is much less agreeable than the first one was, mainly because the quantity on the bottom is not the variable. So we're going to make a u substitution, not for the usual reason, just to make the bottom of the fraction nice. I'm going to let u equal to 3x plus 1, which means du dx is 3, or du is 3 times dx, pretending that these things are fractions, which they're really not. Dx is 1/3 du, and the thing is, we're going to think of these as though they were factors, as though multiplication was going on. The bottom of the fraction, 3x plus 1, is just u. The top of the fraction is x, so I have to solve for x in terms of u, and then just write all the pieces down. U minus 1 over 3 is x, u is 3x plus 1, and dx is 1/3 times du. Thing that people will often make a mistake on is not dealing with that 1/3 du type of thing correctly. Once you've got it written like this, you can take this factor of 1/3 out of the integral. You can take another one out from the numerator. You end up wanting to calculate 1/9 integral u minus 1 over u with respect to u. And see, that's the same type of integral that we were looking at on the previous example. Split it up into u over u minus 1 over u, and carry out the integration as expected. At the end, we put back in the fact that u was just another name for 3x plus 1. As far as I'm concerned, this is a perfectly good way of expressing the solution. Some people will multiply everything out, the 1/9 here, and then absorb the constant term 1/9 into the constant of integration. Some people feel that it looks better if you do that. As far as I'm concerned, it's irrelevant. Previously, we did a u substitution. Our purpose was just to make the bottom of a fraction nicer. You can also do u substitutions in the usual sense of the word. It comes from the chain rule, which says the derivative of f of g of x is f prime evaluated at g of x times g prime evaluated at x. If you take that statement and write it backwards, this is the corresponding interval statement. This makes a strategy for us. Given an integral, if it's not on my list or not something that I can easily manipulate around to make like something on my list, the next thing you think of is there a factor running around in the integrand that looks like the derivative of something else that's running around in the integrand? You would like to look for something whose derivative is g prime. We'll call that something u if we want to make a u substitution. So if I wanted to integrate cosine of x squared plus 5x plus 1 times 2x plus 5, this is not on my list of things I know about. So I look next and think, is there any factor running around in this thing that's the derivative of something else in the problem? And obviously the 2x plus 5 is the derivative of x squared plus 5x plus 1. So we're going to let u equal x squared plus 5x plus 1. Du dx is not a constant now, it's 2x plus 5. So du is going to be 2x plus 5 times dx. And if you'll notice, that's what you've got there. You've got a factor of 2x plus 5 times dx. So I can stop writing it that way and just start calling it du from now on. Here we've done that. The only other thing in this integral was cosine of x squared plus 5x plus 1, and we've made up an abbreviation for that quadratic. What we're trying to calculate is the integral of cosine of u with respect to u. Now that we've made our substitution, that is on the list of things we know about. An antiderivative is the sine of u plus a constant. And then you put back in what u is in terms of x. In section 8.1 of the textbook, there is a table that lists every single integration fact that we know up to this point. I can't actually show you that table on the camera here because of copyright issues, but if you will, open your book up to chapter 8, section 1, and locate that table. Most of the facts should be very familiar to you. A few might be less familiar, and these last three are almost guaranteed to have been forgotten since Calc 1. So I want to look at some examples of these kind of integrals. An integral where you've got radical a squared minus u squared, where we're going to take a to be some positive constant, and u is the variable here. I want to look at this type and that one, and maybe that one too. I want to look at the integral of 1 over square root 16 minus 9x squared. If I think of number a as being 4, 4 squared is 16, so that would match up. I want to think of the 9x squared as being the square of something, which I'm going to call u. And obviously, if I let u equal to 3 times x, then u squared will be 9 times x squared. Just with that, I can rewrite my integral this way. It's literally the integral 1 over square root a squared minus u squared, but there's still a problem. The dx needs to be converted into the corresponding du quantity. So derivative of u with respect to x, the derivative of 3x is the constant 3. So du equals 3 times dx, which means that dx is 1/3 times du. When I write that in, instead of writing dx, I write 1/3 du, and then pull the constant factor of 1/3 out in front of the integral. This now looks exactly like the formula that we were given. So write the answer down. This is 1/3 times arcsine of something. The something is u divided by a. U is 3x, a is 4, and then add the constant of integration. For the kind of problems for which these three formulas apply, you need a little bit of pattern recognition in order to see what you can do. Next, I want to look at the integral of 1 over square root 2x minus x squared. I'm going to manipulate this in a way that's similar to what you did in algebra. I'm looking at that x squared and that 2x, and I'm thinking that's almost a perfect square. So maybe I can get some mileage out of that. Firstly, to keep from getting confused about plus and minus signs, I'm going to rewrite the square root quantity as the square root of the negative of x squared minus 2x. So I don't have to worry about the negative sign for right now. X squared minus 2x, take the 2, cut it in half to get 1, square that, and say to yourself, I sure wish it said plus 1 in there. Now it doesn't. I can write plus 1 though, and then immediately subtract 1 right off again, so I haven't changed anything. This makes the quantity underneath the square root the negative of the square of x minus 1 minus 1. Then I'll bring the negative sign inside the outer parentheses. Negative of negative 1 is 1. So I'm going to be integrating integral 1 over square root 1 minus the square of x minus 1. And see, now it's obvious what kind of change of variables I can think of. The a squared is 1. The u squared is x minus 1 squared. So I ought to have a equal 1 and u equal x minus 1. Using the formula that we were using previously, the antiderivative is the arcsine of x minus 1 over 1, which is just arcsine of x minus 1 plus a constant. Like with algebra, sometimes you have to use some of your trigonometry facts in doing these kind of integrals. So I want to think about the integral of the square of the tangent function with respect to x. I'm not going to need to make any u substitution or anything here. Instead, I have to remember something. I have to remember that cosine squared x plus sine squared x is 1. If you divide through in that equation by cosine squared x, you get 1 plus tangent squared equals secant squared. So 1 plus tangent squared equals secant squared means tangent squared itself is nothing but secant squared minus 1. It would be real easy to go around in circles on these things. The reason that I want to think like this is I don't know an antiderivative right off for the tangent squared, but I do for the secant squared. The antiderivative of secant squared is tangent x minus antiderivative of the constant function 1 is x plus a constant of integration. Sometimes you have to do very tricky algebra and trigonometry techniques. If I want to find the integral from 1 over 1 plus sine x, what you can do is you can multiply the thing you're integrating by 1, except you're going to write 1 very oddly. You're going to write it as 1 minus sine x over 1 minus sine x. When I multiply these fractions together, I'll have numerators 1 and 1 minus sine x. So you just end up with 1 minus sine x above. Downstairs, remembering the old a plus b times a minus b is a squared minus b squared formula, and 1 plus sine x times 1 minus sine x. The result of that is 1 squared, which is 1, minus the square root of the sine of x. Now, at this stage, it might not look like we're making any progress, but we are. Take this fraction and split it up into 2 separate fractions. The reciprocal of the cosine is the secant. So 1 over cosine squared x is secant squared of x, and that's going to be good news for us. So I need to integrate secant squared x minus sine x over cosine squared x. The first part is easy. Antiderivative of secant squared is tangent. The second piece, if you look at it from the point of view that we were talking about previously, something jumps out at you. There is a factor running around in that second chunk of the integral, sine of x, that is the derivative of something else that's in the integral, cosine x. So we're going to let u equal cosine x. du works out to be negative sine x dx. Sine x dx works out to be the negative of du, or negative 1 times du. That turns the integral of that second piece into antiderivative 1 over u squared times negative 1 integrated with respect to u. This works out to be negative 1 over u, which is negative 1 over cosine x. So the integral that I started off with is tangent of x minus 1 over cosine x plus a constant. You can combine the minuses together, or if you think it looks nicer, you can say tangent x plus secant x plus a constant. Coming soon, integration by parts. I think I made a sign mistake on one of these problems. See if you can see where it's at. I'll be talking to you again soon.